This presentation is one of 6 on non-destructive testing. The topics covered by the other presentations are Introduction to Non-Destructive Testing, Penetrant Testing, Magnetic Particle Testing, Radiographic Testing, and Ultrasonic Testing. This presentation is an introduction to eddy current testing. The material is not intended to train individuals to perform NDT functions, but rather to acquaint them with the NDT equipment and methods that they are likely to encounter. Knowledge of the basic principles and typical applications should enable them to know when to call for help from experts. Eddy current inspection uses the principles of electromagnetism, as do several other methods, such as remote field testing, flux leakage, and Barkhausen noise. This presentation will only cover eddy current testing. We will cover the principles of electromagnetic induction, the generation of eddy currents, and some inspection applications. In addition, we will discuss the types of equipment, the advantages and limitations of eddy current testing, and conclude with a glossary of terms. We will cover the principles of electromagnetic induction step by step. When a voltage is applied across a conductor, a current is formed. The current in turn creates a magnetic field in and around the conductor. If an alternating voltage is applied across a conductor, an alternating current and corresponding magnetic field is formed. The strength and direction of the magnetic field follows the current. If there is a free electron in the presence of a changing magnetic field, there will be a force applied to the electron forcing it to move. Thus, if another conductor which is filled with free electrons is brought close to a conductor which is generating an alternating magnetic field, the force on the free electrons in the second conductor will induce an alternating current in the second conductor. As we will see, eddy currents are simply a form of induced currents. Eddy currents flow in a circular path and get their name from eddies, which form in liquids or gases under certain flow conditions. Eddy current inspection uses a probe, which is a length of conductor formed into a coil. Alternating current of a specific frequency is then created in the coil by applying an alternating voltage. The alternating current creates an expanding and collapsing magnetic field, which also changes direction with the alternating current. If a conductive material with free electrons inside is brought near the alternating magnetic field of the coil, the free electrons inside will be induced to form eddy currents in the material. These internal eddy currents will in turn create their own alternating magnetic field. The direction of the induced eddy currents will create a magnetic field which opposes the applied magnetic field. The changing magnetic field from the currents in the material in turn exerts forces on the electrons in the probe coil. Thus, the presence and strength of the current in the material is sensed, if you will, by the probe. The frequency of the applied alternating voltage can range over several orders of magnitude. The choice of frequency is one of the main parameters which affect the nature of eddy current inspection. The induced eddy currents in the material are distributed in width and depth inside the material. The currents are strongest at the surface and decrease exponentially with depth in the material. One standard depth of penetration for eddy currents is the depth at which the strength is 37% of the surface strength. This percentage is a consequence of the base of natural logarithms. The depth of penetration is inversely proportional to the square root of the product of the frequency, material conductivity, and material permeability. This slide illustrates the effect of varying the frequency, conductivity, or permeability on the distribution of the eddy current strength. The wide dark bar indicates one standard depth of penetration, or skin depth. The depth is deeper for lower frequency, conductivity, or permeability. The operator sets the instrumentation to generate the frequency of the currents in the coil. The conductive material being tested has an effect upon the coil based on the amount of material near the coil or the conductivity or permeability of the material. The eddy current instrumentation measures changes in the voltage or current in the coil. Basically, the electrical impedance is the feature of interest of the coil. Impedance is a combination of resistance and inductance. Changes in these two features can be related to changes in the conductive material being tested. This slide illustrates the effective impedance of a coil. Whatever the opposition to current flow, it can be expressed as a series combination of the resistance and inductance. Let's define these terms. Resistance is the opposition of current flow, resulting in a change of electrical energy into heat or another form of energy. Inductance, or inductive reactance, X sub L, is resistance to AC current flow resulting from electromagnetic induction in the coil. Impedance Z is the combined opposition to current flow resulting from inductive reactance and resistance. Eddy current inspection can be used for a wide variety of applications. The left image shows crack or corrosion inspection on an aircraft. The right image shows inspection of heat exchanger tubing. Thickness measurement is one application for eddy current testing. The limitation is that the frequency of excitation of the eddy currents must be able to penetrate the thickness of interest. Typically, this means that the skin depth should be on the order of the material thickness. Thicker materials can support more eddy currents than thinner materials, and thus a measurement of the strength of the eddy currents can be related to the material thickness. This slide illustrates the amount of eddy currents present in different thicknesses of material. The strength of the eddy currents will be larger for the thicker material because more eddy currents can be supported. Eddy current thickness measurement is often used to detect material loss due to corrosion and erosion. This method is especially useful in the aviation industries because aluminum is highly conductive but not magnetic. Iron-based materials have a large permeability which makes deep penetration of the eddy currents more difficult. Eddy current inspection is used to inspect tubing for corrosion and erosion. The probes are designed to be inserted into the tubing. Besides thickness changes, the method can also detect other geometrical changes, such as dents. This type of inspection is routinely used to check the tubing in heat exchangers. Eddy current inspection is especially well suited for detection of cracks in conductive materials. The presence of a crack disrupts the flow of current and thus decreases the strength of the eddy currents. The change in strength can be detected by scanning techniques. This slide illustrates the change in the eddy currents due to the crack. Since the eddy currents decrease in strength with depth, the method is most sensitive for surface breaking cracks, or cracks very near the surface. Crack location is usually determined by scanning with a small size probe. In some cases, with identical parts, a single large coil designed to match the part can be used to detect the difference between defective and crack-free parts. Thus, a single encircling coil may be used to check a shaft, for example. Many eddy current probes are especially designed to fit the geometry of interest. For example, a probe molded to fit the shape of the bead seat on an aircraft wheel can be used to detect cracks. This particular inspection has been performed by the CTC NDE laboratory for the Cummins corporate jets. Many holes can develop cracks either because of high residual stress, the presence of material defects, or fatigue. Special side-looking coils can be rotated and translated using probe guns to perform hole inspection. This type of inspection has been performed at Cummins for injector nozzles and other tubular structures. When the eddy current coil is far from the material being inspected, the coil has a fixed impedance. This impedance changes as the coil comes closer and closer to the material. Thus, the coil can detect the presence of the material. The change in impedance is largest when the coil is in contact with material. The change in impedance as the coil is lifted from the material is referred to as liftoff. If the liftoff is caused by non-conductive coating, then the thickness of the coating can be measured. The impedance of the coil can be correlated to the coating thickness using calibration standards. This method is capable of measuring very thin coatings. This slide illustrates the effect of probe distance from the material on the eddy currents produced. The probe is placed in contact with the surface of the coating, and thus is the coating thickness away from the conducting material. This slide illustrates the different signals obtained from different thicknesses of paint on aluminum. The signals are a direct function of the coating thickness. As we mentioned before, the eddy current response is a function of the conductivity and permeability of the conductive material. Thus, the eddy current method can be used to measure these properties. These properties can be used for various purposes. Some uses include material identification, material sorting, detection of heat damage, measurement of cladding or plating thickness, measurement of case depth, and heat treatment monitoring. All of these applications depend upon a change in conductivity or permeability. Eddy current methods were used to measure the uniformity of conductivity in the Liberty Bell in Philadelphia after the bell was attacked by a visitor using a hammer. There are many types of eddy current equipment. The equipment may be special purpose or general, but consists of instrumentation, probes, and reference standards. Some instruments are simply either analog or digital meters. These measure either phase or amplitude of the signal and rely on calibration standards. The standards illustrated in this slide consist of materials with known conductivity. The meters are usually specifically designed to measure one specific feature, such as conductivity or thickness. I remember years ago using a meter to search for 10,000 improperly aged rivets on the first DC-10 aircraft. Even though the display is a simple meter, these instruments can still be used for several different types of measurements. More training is required for the proper use of this equipment compared to equipment which displays both the resistance and inductance of the coil. Some meters are specifically designed and calibrated for a specific function, such as measuring conductivity. Simple meters without special purpose scales can perform more tests, but require reference standards and data extrapolation techniques to obtain quantitative data. Many eddy current instruments are battery powered and easily portable. Since the coil response consists of two components, resistance and inductive reactance, the response is often displayed on an impedance plane. Each point on the plane corresponds to a specific combination of resistance and inductance. The point on the impedance plane changes as the impedance of the coil changes. These changes can be used to detect many different conditions. When the coil is not near the conductor, the point on the impedance plane is often referred to as the air point. Magnetic materials, those that are capable of being magnetized, will have final impedance points with higher inductance values than non-magnetic materials. The impedance plane also shows the directions for liftoff, conductivity, permeability, and cracks from the endpoint for a given material. Thus, the impedance plane shows all the information which is available. This information can be used to sort materials, measure conductivity or permeability, measure liftoff, and detect cracks. The two-dimensional display considerably increases the information that is useful for interpretation and analysis. This type of information can also be created for different frequencies of excitation. The frequency which leads to the best measurement method can then be determined. Some digital impedance plane instruments are capable of driving and displaying two different frequencies at the same time. This can be useful if one frequency alone is not capable of detecting all conditions of interest. Some of the most interesting and powerful modern instruments can generate and analyze up to 8 simultaneous frequencies, spanning a very large range of equivalent skin depths. These instruments are capable of detecting many different material conditions. As a general rule for eddy current inspection, all parameters which affect the eddy current response should be kept constant except the one feature of interest. Otherwise, the interpretation of the data becomes very difficult, if not impossible. Many instruments include methods of recording or displaying the results versus time. This slide illustrates a couple multi-frequency eddy current instruments. Not only are some instruments capable of multiple simultaneous frequencies, but many can drive many different probes at the same time as well. These instruments are often used in the power generation and petrochemical industries. The multi-frequency instruments collect more information, permit comparison of the same discontinuity with different frequencies, allow mixing of signals to reduce noise, and improve many capabilities. This slide illustrates one method of displaying the multi-frequency information. The impedance plane displays the different frequency responses in different colors. The strip charts display the time variation of one component of specific frequencies. Even more than ultrasonic inspection, special purpose eddy current coils are designed for specific applications. Thus, there are thousands of potential choices. Many times an application will require a special design just for the application. Some probes are point probes, some are encircling, some are differential probes, which compare the outputs of two coils. Some are side-looking for use inside holes. The factors to consider for probe selection include the material penetration requirements, surface versus subsurface, the sensitivity requirements, the type of connections, the probe and instrument impedance, the probe size, and the probe type. Probes are generally classified as either surface probes, inside diameter probes, or outside diameter probes. Surface probes mount the coil near the end of the probe and are moved by the operator over the surface of the test article. The coil diameter may be small or large and depends upon the operating frequency. Some probes have spring-mounted coils or special holding fixtures to keep the coil in the proper orientation or position. Some surface probes are designed for crack detection of holes. Surface probes can be very small to use in confined areas. This slide illustrates a probe designed to fit on the end of a finger. Inside diameter or bobbin probes are primarily designed for inspection inside tubes or cylinders. Outside diameter or encircling probes are designed to surround the test article. These probes are used to inspect anything with circular symmetry, including bars and tubes. There are many different types of reference standards. Different materials are used for conductivity standards. Various holes or EDM notches are used to calibrate for crack detection. Various thicknesses are used for thickness measurement. The eddy current response is a very complex function of the affecting parameters. Reference standards permit comparison to known values and are typically manufactured from the same material as the test article. Because of the large number of different applications, there are many different types of standards. This slide illustrates some material thickness standards. Crack standards come in a variety of shapes and sizes, which is controlled by the inspection application. The material should be the same or very close to the material of the component being tested. EDM notches are often used to represent cracks, but it should be noted that EDM notches usually give a stronger signal than a crack will. The image on the left has EDM notches of various depths, and the two on the right showed EDM notches at fastener holes. This ASME tubing pit standard has holes and grooves machined at different percentages of the wall thickness. This coating standard has various known thicknesses of paint on an aluminum substrate. Eddy current testing has the following advantages. Eddy current testing is sensitive to small cracks and other defects. It detects surface and near surface defects. The method gives immediate results. The instrumentation and probes are very portable. The method can be used for many applications besides flaw detection. Only minimum part preparation is required. The test probe does not need to contact the part. Eddy current inspection can be performed on complex shapes and sizes of conductive materials. The limitations of eddy current inspection include only conductive materials can be inspected. The surface must be accessible to the probe. The skill and training required is more extensive than for other techniques. The surface finish and roughness may interfere with inspection. Reference standards are needed for setup. The depth of penetration is limited. Flaws such as delaminations that lie parallel to the probe coil winding and probe scan direction are undetectable. The following glossary of terms defines some of the terms used in eddy current testing. Alternating current is an electrical current that regularly reverses direction. Analog refers to data which is represented by continuously variable physical quantities, such as a watch with hour and minute hands. ASME is an abbreviation for American Society of Mechanical Engineers. This society is highly involved in establishing and maintaining industrial standards. CRT, of course, is an abbreviation for cathode ray tube. It's a vacuum tube that uses one or more electron guns for generating an image. Calibration is adjustment of a test system response using known values so that unknown quantities can be derived. Conductor is a material capable of allowing electrical current to flow through it. Discontinuity is an interruption in the physical structure of a part. Cracks are examples of discontinuities. EDM is an abbreviation for electrical discharge machining, which uses an electrode and electrical current to remove metal. This method is sometimes used to prepare calibration standards for eddy current testing. Electromagnetic induction is a process which creates electrical current flow when a dynamic magnetic field is brought into close proximity with an electrical conductor. Extrapolation projects or predicts unknown values from known quantities. IACS is an abbreviation for International Annealed Copper Standard. This is the standard unit of measurement of electrical conductivity in eddy current testing, with pure annealed copper as the standard, measuring 100% at 20 degrees Celsius. Impedance plane diagram is a diagram that depicts the changes in electrical impedance that occur in an eddy current coil as test variables change. Multiplexing is the use of a time-sharing system in which a coil is stimulated at several different frequencies, one after another, for a certain amount of time. Results from each stimulation can then be processed and displayed. Permeability is the ease with which a material can be magnetized. It is the slope of the magnetization versus applied magnetic field curve. Probe is a common term used in eddy current inspection that refers to the test coil.